In this lesson, we'll talk about operations on sets and compound inequalities. First, let's look at what kind of operations we can perform on sets. Sets can be added by taking union of two sets. Suppose we have the set of points in this loop, call it A, and another set of points in the other loop, call it B. The union of these two sets is everything what's shaded in A and B all together. And this union will be marked by the sign similar to U, like this. So union or sum of two sets A and B is a new set of all points X that belong either to the set A or to the set B. The connecting word here is OR. That's important to remember. A point that belongs to union of two sets must belong either to the first set or to the second set. Okay, what else can we do with sets? We can multiply them, creating a new set that is called intersection or common part. So, product, intersection, or common part of two sets is defined by the overlapping part. A point belongs to the intersection of two sets, marked by upside down cap like this, must belong to both sets, A and B at the same time. So this time we're using the connecting word AND, in opposed to OR. So again, union of two sets represents everything what's in both sets altogether, and the product of two sets is the overlapping part. There is one more operation that we can perform on sets. It is a subtraction. Obviously, the result of subtraction is called difference. So, for example, if we have set A here and set B, the difference of A minus B is all those points that are in A, but they are not in B. Since we subtract sets, we use slightly different sign than just a regular subtraction for numbers. The subtraction sign we're going to slant downwards like this. So A minus B is a set of all elements that belong to A and at the same time do not belong to B. So in algebra of sets, we can perform those three operations: union, intersection, and subtraction. Let's practice on particular sets. If A is a set of four numbers, 1, 2, 3, 4, B is a set of three numbers, 1, 3, and 5, and C is a set of just two numbers, 5 and 6, we need to find intersection of A and B. Since intersection is a set of points that belong to both sets A and B, we are looking for the overlapping elements. For example, 1 is in both sets, 3 is in both sets, and those are the only numbers that appear in both sets. Therefore, the common part of A and B is composed of 1 and 3. In example B, we are asked for the sum, union of A and B. That means we need to list all elements that are either in A or in B. Okay, we can go 1, 2, 3, 4, that's for sure, because those points are in A. And what else do we need to take from B? 1 is already taken, 3 is taken, but 5. However, 5 wasn't, so we need to include 5 in this set. Okay, now A subtract B. We need to take everything what's in A, but not in B. Since 1 and 3 was in B, those numbers can't be taken. Therefore, A minus B is just 2 and 4. The next example is B intersected with C. So the common part of B and C is just 5. So it's a one-element set composed of 5. Intersection of A and C. Let's erase our previous markings. Intersection of A and C is a common part of A and C. But notice there is no common number, because those numbers are lower than 5 and those are higher or equal than 5. Therefore, there is no element in this set. We need to write an empty set. Now, A union B union C. I'm sure you can finish this on your own. Try it. that will be everything what's in A, or B, or C, which means all the numbers 1, 2, 3, 4, 5 from B, and also 6 from C. All the numbers from 1 to 6. Okay, what about intersection of A, B, and C? Common part of the three sets. Well, since we already know that common part of A and C is an empty set, then common part of A, B, and C, it must be an empty set as well. There's no number that belongs to all three sets. And finally, C intersected with an empty set. Well, since there's no element in an empty set, we can't have any element in the intersection of these two. So it's also an empty set. Now let's try to apply it to intervals. In the first example, we have two intervals. One is open and the other is closed. Let's draw those intervals on the number line. I will mark the first interval in green from -1, let's say here, until 3 without the endpoints. So that's my green interval here. And then maybe in purple the second interval from 2, which is below 3 somewhere here, cover dot 2, until 5. Okay. Now, what's the common part, intersection of these two? Well, let's mark it in red. Those are the points that are marked in green and in purple. So that's the set from 2 to 3. Should we take 2? Well, yes, because 2 belongs to this interval and also belongs to that interval. So it's common for the two. Okay, therefore our answer should be starting from 2 until 3. Should we take 3? No, because 3 did not belong to the green interval. So from 2 to 3, half closed, half open interval. Let's try B. Notice that we work with exactly the same intervals, so we could actually look at our previous diagram. Since this is union, we're taking everything what's in green or purple. Therefore, this interval will be from -1 till 5. Everything from here to there. So -1, 5, and just double check the endpoints. Well, since -1 does not belong to the green, we need to use the round bracket. -1 is not in the union. However, 5, it did belong to the purple interval, so we include 5. Half open, half closed interval. Okay, let's look at example C. You may want to try it on your own first. Again, I'm going to mark the first interval from -infinity until 5, including 5, in green. Those are the points here. And the purple integral from -3, which is below 5, and again, the -3 is included in the purple set. Everything what's here. We are taking intersection, the common part of the two. So that's from -3 until 5, the overlapping part, with both endpoints, because both of them were included in both intervals. So the answer is from -3 till 5. Try another example. First interval is from -infinity until -3. Let's say -3 is here. Cover dot, this set. And the purple set will be from -3, again, is included, until infinity. Okay, so what's the intersection? What's the common part? Well, the only common point that is both green and purple is the number -3. Therefore, this is the only solution here. Since this is just one single point, we'll record the answer in a set notation. We just list this one element -3. It would be very artificial to write an interval from -3 to -3. Remember, intervals corresponds to segments, and interval from -3 to -3 will represent just a point, so it's like a degenerated segment. We avoid writing like this, so we don't write something like this. If it's just one point, it's better to record this in a set notation. Okay, let's look at the following example. Now we have a segment from negative infinity until negative 3 including negative 3. So that's our green set. And a segment from negative infinity until 5, which is farther than negative 3, somewhere to the right. However, 5 is not taken, hollow circle. So purple set would be this one. Okay, so what is the intersection of these two sets? It is the overlapping part, both purple and green. Therefore, it's everything from minus infinity until negative 3. Can we take negative 3? Yes, we can, because negative 3 is both green and purple. So the final answer is from minus infinity, round bracket, till negative 3, square bracket. And finally, let's draw this. Notice again we have exactly the same intervals, so we could even look at this picture, but because it's a special case, let's draw it again maybe. From negative infinity until negative 3, including negative 3, that's this set, and the purple set until 5, without 5. But this time we're looking for the union of the two sets, not intersection, union. That means everything what's in green or in purple. So we can go from minus infinity until 5. Minus infinity until 5. 5 is not taken, so round bracket on each side. Now we are ready to solve some compound inequalities. What are compound inequalities? Those are systems of inequalities with connecting word, either and or. And here are some examples. If we want to indicate that x is bigger or equal than 2, but at the same time is smaller than 3, we can write this compound inequalities, two inequalities in a row, in one stream like this, or we could rewrite those two inequalities equivalently by saying x is bigger or equal than 2 and at the same time x is smaller than 3. So writing in one stream like this is just more compound way of representing our two inequalities. And if it's written in one stream of signs, the two inequalities are connected by the word and. However, we may have another case. We may indicate two inequalities but connect them with the word or. To solve this system of inequalities, first we're supposed to find the solution set for the first inequality, possibly graph it, then find the solution set for the second inequality, graph it, and then or represents union of the two solutions. So the final answer will be the union of these two solutions. While in here, when the connecting word is and, the overall answer will be the intersection of the two solutions, of the solution of this inequality and that inequality. For example, in this case, the numbers that satisfy these two compound inequalities are such that they are larger or equal than 2, meaning that we are looking for numbers to the right of 2, including the 2, and at the same time our number is supposed to be smaller than 3. So we are looking for numbers that are smaller than 3. Since the connecting word is and, the intersection of these two sets will be from 2 to 3, the common part, both orange and blue. Obviously with the 2, but without the 3. So in this case, if we want to write our solution set in interval notation, we would say from 2 to 3, excluding the 3. And the second solution set, here we mark all the numbers that are less than 2, which are to the left of 2. Then we mark all the numbers that are greater or equal than 3, to the right of 3. And since or corresponds to the union of these two sets, the answer for this system of inequalities will be from minus infinity until 2, round bracket, and then union from 3 to infinity. Notice that in this case, we can't write a single interval because the solution set is actually composed of two segments. So we need to indicate both of these segments and connecting them with the U sign. However, in the system of inequalities that are connected by the word and, the solution will be usually represented by one segment, so the answer can be stated in one interval. Okay, let's try to solve our first compound inequalities. How do we solve it? Well, our goal is to leave the x by itself. So we want to get rid of both numbers, 3 and -1. Which of these two numbers should we take care of first? Well, the same as when solving equations, we're undoing the addition or subtraction first, before we start dealing with multiplication or division. Okay, therefore let's add 1 to all three sides, and then we'll have 2 plus 1 is 3. This 1 will cancel the -1, so we have 3x, and 5 plus 1 is 6. At that point, to be closer to x, we're dividing by 3 to get rid of this leading coefficient. So 3 divided by 3 is 1. This 3 is cancelled, so we have just x, and 6 divided by 3 is 2. It's always a good idea to draw it on the number line so you can see what's going on. The numbers that we are looking for will have to oscillate between 1 and 2. So if I mark 1 here and 2 over there, the solution set is everything that's in between. So I'm ready to give the final answer. X is any number from 1 to 2. Okay, now notice that these two inequalities could be written as two separate inequalities with the connecting word and. Obviously, when solving, we'll perform exactly the same operations. So we're adding 1 to both sides, that will be 3 smaller than 3x, and dividing by 3, so x is bigger than 1. Copy the word and change the second inequality the same way. Add 1, so we'll have 3x smaller than 6, divide by 3, so we'll have x smaller than 2. The word and still stays there. So if I want to represent this two inequalities on the number line, it will look like that. Let's say 1 is here. X's are larger than 1, so x's are going this way. And x's are smaller than 2. Let's change the color. X is smaller than 2 are going that way. Okay, so what is the solution set? Obviously, those are the numbers that are both blue and purple. That means the numbers between 1 and 2. Since 1 is not taken in the first inequality, it has to be hollow circle, and 2 is not taken in the second inequality, still hollow circle. Therefore, this is our final solution set. Obviously, it's the same as when solving simultaneous inequalities written like this. That's why as long as these two expressions are exactly the same and inequalities are going in the same direction, then the and situation can be written in a shorter way, simultaneous inequalities written in one stream. Notice that this can be done only when the two inequalities are really going in the same direction. You can't do it when one inequality is like this and the other like that. For example, if I would have the information that x is larger than 1 and also x is larger than 3, well, this really gives me one inequality, because if x is larger than 3, then obviously it's larger than 1. Therefore, this inequality doesn't introduce any new information, so it's not a good way to write. Similarly, if the inequality will go in different direction that way, we could say x is smaller than 3 and x is smaller than 1, but what does it mean? If x is smaller than 1, obviously it is smaller than 3. Again, this inequality will not give us any more information, so it's actually just one inequality. So remember that simultaneous inequalities are always written in one and the same direction. Okay, let's try the second example with the connecting word or. Now notice that this time, even though we have exactly the same expression here and there, 3x minus 1, we can't write it as simultaneous inequalities like this. Why? Well, because if we write like this, we indicate that the connecting word between these two inequalities, this one and that one, is actually and, which is not the same as or. So we are not writing it simultaneously. This way of writing belongs only to the cases when the connecting word is and. Okay, let's try to solve it. What we need to do is to leave the x alone. So let's move the 1 to the left by adding 1 to both sides. That will be 3 bigger than 3x. And then divide by 3. So we end up with x smaller than 1. Keep copying the connecting word or, and similarly as in the previous inequality, we need to add 1 to both sides to get closer to x. 5 plus 1 is 6, and then divide by 3. So x is bigger equal to. Connecting word is or. So let's draw it on the number line. X is smaller than 1. They are going this way. And x's that are bigger equal than 2. Start with 2 and go to the right. That's a purple set. Therefore, our final answer for these two inequalities will be the union of these two segments, which means we go from the left, from minus infinity until 1 without 1, and then union with the second segment, which starts with 2 and goes until infinity. Okay, I hope you've got it. Why don't you help this stick figure to solve the simultaneous inequalities? Okay, on the previous slide, we mentioned that the connecting word and usually results in one segment, one interval as a solution. Let's see if this will be the case in this example. Let's solve for x the usual way. Move the 5 to the right. That will be negative 7x bigger than 19 minus 5, which is 14. And then we need to divide by negative 7. Well, remember, red alert, as soon as we divide by a negative number, we need to switch inequality into opposite. So we'll get x smaller than 14 divided by negative 7 is negative 2. Copy the word and let's do the same with the second inequality. Subtract 2, so we have negative 3x smaller than negative 4 minus 2 is negative 6. And then we need to divide by a negative number, negative 3. So the inequality reverses to bigger, and we have x bigger than negative 6 divided by negative 3 is 2. Okay, how do we see it on the number line? X is smaller than negative 2. That looks like this. And at the same time, x's are bigger than 2. So 2 here and bigger than 2. Well, therefore our solution is, what do you think? What would it be? We have a connecting word and, so we're looking for intersection of these two sets. But there isn't any. So the solution is an empty set, or you can say no solution. There is no point that will satisfy both inequalities at the same time. Okay, let's look at this example. This time the connecting word is or. Let's see. To solve for x, we add 4 to both sides. We have 4x smaller than negative 8 plus 4 is negative 4. And then divide by 4, we end up with x smaller than negative 1. Keep writing or and solve the second inequality. 4x, add 4 to the other side, so we have smaller equal 12 plus 4 is 16. Divide by 4, we end up with x smaller equal 4. Okay, let's draw it on the number line. A set of points that is smaller than negative 1 is marked here in blue, or the set of points that is smaller equal than 4. That will be 4 covered dot because it's included, and everything that is smaller equal goes this way. So that's the purple set. Now let's make sense of it. The connecting word is or. Or means union of these two sets. So observe that the purple set is overtaking the blue set. The purple set is larger and it includes the blue set. So the final answer here would be everything from -infinity till 4 inclusive. X can be any number less or equal than 4, meaning this inequality didn't produce any extra solutions. It was enough to take solutions from the second inequality. And the last example, again the connecting word is or. Let's solve the first inequality. Add 7 to both sides. We have 3 plus 7, which is 10. And then divide by 2, x becomes bigger equal 5. Copy the or. Here, to solve for x, well, notice that we could move this negative x to the right, and then x would be positive. Then we wouldn't have a problem with switching inequality sign because of the negative sign. Let's keep the 7, and yes, it's done already. So x is bigger equal 5 or x is smaller than 7. Let's picture it out on the number line. X is bigger than 5. Let's say 5 is here, covered dot because of the equation. Everything that's bigger than 5 is over there. And in purple, x is smaller than 7, smaller equals 7. So 7 and anything that is smaller than that. Okay, let's make the conclusion. Since the connecting word is or, we're taking union of these two sets. So what would be the answer? Well, it's everything on the number line, so x can be any real number. The answer is all real numbers in this case. So those are the special cases. Why I call them special? Because normally when you have a connecting word and, you would expect just one interval of some sort. But in this case, the overall answer is an empty set. So this usual overlapping segment simply disappeared. There wasn't anything overlapped. Second example, usually when we have two inequalities connected by or, we would expect two segments in an answer with the union. But in this case, we end up with one segment, because the other blue segment was actually a subset of the purple one. And one more example with or. This time, since the two segments overlap, when we take the union of those two segments, we end up with all real numbers, with entire number line. And finally, one application problem. Let P represent the percent of children covered by private insurance, which is represented by this first white column. M, the percent covered by Medicaid, which is represented by the second pink column. And N, the percent not covered at all, which is represented by the third green column. Using the information from the table, give the years that the following is true. Okay, question A calls for private insurance P being bigger or equal than 68. So let's mark which years are actually solutions to this inequality. Bigger equals 68, that's this one, and that's all. Therefore, solutions to the first inequality would be just these 2 years, 1998 and 1999. However, we have a connecting word and we need to solve the second inequality. The percent covered by Medicaid is bigger equal 18. Okay, so in the pink column, the numbers that are bigger equal 18 are this one, and that one. Therefore, these 3 years are the solutions to the second inequalities. Okay, so we have the situation. First set is composed of these 2 years, and the second set is composed of these 3 years. So since the connecting word is and, we're looking for intersection of these two sets, which means just 1999. Therefore, the answer is 1999. Only this year satisfies these two conditions. Let's try the second question. Here we have exactly the same inequalities. The only difference is we're taking or. So we're using the same sets of years, but this time we're taking or. Well, that means we're taking all 4 years. Therefore, the answer here would be 1998, 1999, 2000, 2001, all 4 years. I'll put a bracket here as well as a set composed of 1 year. Let's try to look at the next question. We're looking for years in which the percent of children covered by private insurance is more or equal than 67. So more or equal than 67 is actually happens in all 3 of those years. Happens in these 3 years. And the percent of children not covered by any insurance must be smaller or equal than 12.5, which means, look at the green column, it must be smaller than 12.5. Oh, that looks like all of these years. Okay, so since the inequalities are connected by the word and, we're looking for the intersection of the sets of those years. So these 3 and those 3. The intersection are the years 1999 and 2000. And finally, again, both inequalities are exactly the same, but the connecting word is or. So in this case, similarly as in B, all 4 years will satisfy the condition from 1998 till 2001. Thanks for watching.